Okay, thank you very much. It's a great pleasure to be here. I learned game theory in self-defense a couple of years ago, so I am learning a lot in this conference. Uh, I come from probability and population genetics, so please forgive me if I miss some important reference, and I'm very happy to learn from all of you about these very interesting topics. So what I'm going to do today is say a couple of words about population genetics. I will introduce the way I think about game theory in the framework of population genetics. That's the coloring rules. And then I will discuss something about dormancy, which is how genes can somehow jump a lot of generations, and that this change the picture in a population genetics framework. And I will finish combining dormancy and game theory, and with some final remarks. So to start talking about population genetics, the zero model is the Wright-Fisher model. So we have fixed population size, n individuals per generation. Each column is a generation. Each vertex is an individual. And the only rule is that each individual choose a mother uniformly at random from the previous generation. If we have this Wright-Fisher model, we can put types at some generation that we call zero, and we can add the rule, which is the simplest possible rule, that each individual copies the type of its mother. And this implies that if we color generation zero, there is a coloring induced in the rest of my infinite graph. So one thing that we can do and we like to do is to count the frequency of individuals of certain type. So we can count the frequency of red individuals as this change through time. So the stochastic process that I want to consider is the number of red individuals divided by n, which is the population size. And this is a nice stochastic process with some binomial way of going from one generation to the next one. So it's just a nice Markov chain that we call the frequency process. Something that we like to do a lot is consider scaling limits. So n is the population size. And what we do is send the population size to infinity and speed of time in a particular way. So we find some interesting limits. So this is a very famous result. The scaling limit of the frequency process is the Wright-Fisher diffusion, which is, if you want, is a time change of the Brownian motion. So this is just saying that it's something that moves without a preferred direction, and it moves a lot in the center, and it moves very little close to the boundaries, and actually at some point it touches one of the two boundaries, and it stays there forever. So that's the Wright-Fisher diffusion. So if we want to talk about population genetics, of course, we want to talk about selection. Wright and Fisher also introduce a very nice way to think about selection, which is simply consider that there are two types, red and black, and maybe the red individuals have selective advantage. So we give weights to black individuals. The weight is 1 minus s, right? And then what we say is that each individual chooses its mother from the previous generation, but this time the decision is made proportional to the weight, right? So it's just the probability of being red is 1 divided by the total sum of the weights in the previous generation. So that's the way Wright and Fisher thought about selection, and we can play exactly the same trick as before, measure time in units of population size, sending population size to infinity, and what we obtain is the Wright-Fisher diffusion with selection, which is contains things that you would like. So it's just, if you see this first part is simply the logistic equation, right? So if there is no noise, what you get is the logistic equation. So the way to think about this is a logistic equation plus noise. Right? So that's how Wright and Fisher thought about selection, but there are different ways of thinking selection. One that I really like was introduced by Cron and Neuhauser 25 years ago in this beautiful paper that I strongly recommend. And the idea is you have, maybe you can think of generations, or you can think of continuous time moral model. And what you do is some individuals have more than one observation in the previous generation, right? So for example, this individual here observed these two individuals, and there's a preference rule that says red is preferred over blue, over black, right? So it's another way to think selection, which is I observe some part of the population in the previous generation, and I choose my favorite, right? So what we did with Dario Spano some years ago was take this idea from Krohn and Neuhauser and do it in the Greit-Fisher model. So basically, you now really live in generations, and you have a number of potential ancestors in the previous generation. So each individual samples independently a number of observations, and then there is a preference rule saying, basically, if you observe at least one red, you will be red, right? So, for example, this individual sampled 3 observations in the past, and then because it observes one red, it will be painted red, right? Mathematically, this way of thinking selection is way nicer because it has very nice duality properties. Biologically, maybe Mike will say you are not allowed to define selection wherever you want, right? And maybe I will say to Mike, well, I am because I am a mathematician, so I have an open relation with reality. But because he is the boss, I cannot really say that. So I need to convince him that this is really a good way of thinking selection. And it turns out that the way that you choose the number of observations from the previous generation can lead to some interesting notions of selection or to some very crazy ones. So what we observed is that if the number of observations from the previous generation is geometric with parameter 1 divided by s, what you recover is exactly the Greit-Fisher model with selection. Right? So this is no approximation at all. It's just a different way to think the classic Greit-Fisher model with selection. So a particular example of this potential ancestor story is the superclassic Greit-Fisher model with selection. Okay, so now that we have this model, as a mathematician, we can start generalizing every piece of it, right? So we can generalize the way that you choose your sample from the previous generation, but you can also change the rule of what do you do with the observations that you have, right? So the rule so far is if you see red, you take red, but we can do something different. So this is called the coloring rule, and that's the simplest possible coloring rule. If you see the best type, take the best type. And it will be related to a utility matrix in game theory. And well, here, if we go back to a random number of potential mothers, what we will have is frequency-dependent selection. So let's try to discuss a bit more about this coloring rule. So what we do is, in this paper with Charlene Smadi, what we did is you do exactly the same construction. So you look back, take some number of observation, and choose something according to a coloring rule that you give to yourself. So there are many coloring rules that make sense. For example, you can take majority rule. If you have more black observations than red, then you color black, right? You can have minority rule. You can have, well, you can basically invent your own rule. So you can have a crazy rule that probably doesn't make sense. So if you observe 2 black individuals, then you are black, otherwise you are red, right? So you can basically give yourself any coloring rule that you want. And some coloring rules are related to interesting processes that are studied in the literature. For example, majority rule is related to the Alan Kahn model, which is used to study hybrid zones in math biology. And another interesting case is if you only allowed to observe either 1 or two potential parents from the previous generation, then you can express the coloring rule as a matrix, and there is a very clean connection with game theory. So you can, for example, if you live with 3 types, you can have more, but you can give yourself a matrix of this type, P12, and here 1 minus P12 in the reflection. And what this means is if I observe red and blue, then it will be blue. It will be red with probability 1 minus P23, and it will be blue with probability P23. Right? So I have my matrix, and this induces immediately a coloring rule. A particular case of this is if we only live in zeros and ones, meaning if I look at red and blue, then my matrix says always take red, right? So it's reminiscent of the previous discussion. Is a deterministic coloring rule, and all the randomness is in who do you observe in the previous generation. These are called tournament selection because these matrices are just incident graphs of a tournament graph, right? So these graphs are called a complete directed graph is called a tournament. So this is why it's called tournament selection. And you can do it for many types. So this is a tournament for 5. And you, of course, can do it for more. This is the matrix that you get for a tournament of size 5. This is a tournament of size 9. And you can play with that. So in the case of 3 types, there are only 2 possible tournaments, right? One tournament is this one that says red always win and otherwise blue, right? So this is very similar to usual selection. And what would you think the other tournament be, right? So the other tournament is nothing else than the famous rock, paper, scissors story, right? So it's 1 wins against 2, 2 wins against 3, and 3 wins against 1, right? So it's just a way to think these classical things. And we can go back to the model, to the Great-Fisher type model. So we have 1 generation. We want to construct the next one. And basically, everybody do observations in the past, and your coloring rule tells you how to paint the next generation. For example, this individual observed the sneaky lizard and the angry lizard, and then it becomes sneaky. So, well, the classic limit theory of population genetics allow us to obtain equations like this. So you have some part that comes from the coloring rule that we decide, and some part that comes from the noise of the model, right? So this is just a replication equation with stochastic part that was explained very nicely yesterday. But what we have here is the game theory part and the population genetic part. And of course, this is just another way of obtaining things that had been seen in the literature before, in particular by Arne, but also in different publications. So why do I think this is nice? Well, thinking in terms of the Great-Fisher model allows us to measure quantities. So it's very compatible with experimental evolution, for example. So we can really bring parameters from experiments or from the literature. And also, there is a huge literature of scaling limits for population genetics. So if we write this in these terms, we can put on top our favorite scaling limit in some other direction, right? So it's kind of another piece of a puzzle that you can now make slightly bigger. And I want to expand on this second idea. So I want to show you how to put something on top of this model, something that is well known in population genetics. And that's dormancy, which is something I chose because it's a topic that I have been working a lot. So in my PhD, I introduced the seed bank coalescent, which is a way to think dormancy in a very practical way. So imagine that you have some bacteria. Typically, the bacteria get their mother from the previous generation, but it could be that these bacteria produce some cyst or some spores or something, and these cysts persist in the environment hundreds or maybe thousands of generations. Right? So what you have is very big jumps in the genetic information. And this is a nightmare from the point of view of mathematics, because the Markov property is lost forever. Right? So if we look at how types propagate, for example, here, the orange type is super happy. They have invaded everything. But then there is a jump from the past that reintroduced the blue population. This thing is related to the fractional Brownian motion and to things that are a bit complicated. But what I did in my PhD is observe that, again, the geometric distribution is fantastic. So if we assume that these jumps to the past are geometric, then the system reduces enormously, and you get something that is, again, Markovian and converge to a two-dimensional diffusion. So this non-Markovianness becomes trapped in a two-dimensional Markov process. One part is telling you about the tail, about the information from the past, and the other is telling you about the present. And this is good because this is very nice to study at this point. So this diffusion is similar to the Great-Fisher diffusion. It's two-dimensional. It starts moving in the diagonal like this, and eventually it hits one of the boundaries and gets absorbed there forever. I had been obsessed with dormancy, so basically what I do is take some nice model, put dormancy on top of that, and then very nice things happened. And this is exactly what I did with the game theory story that I'm telling you now. So, okay, we can take the lizard story and put dormancy on top of that, right? Why would this be interesting? Well, the lizard story had been intensively studied, and one of the observations is it should not be there, right? So theoretical models say that these cycles would crash with the boundary, and we would lose one of the types, and then everything will be gone. However, it was explained by Kerr et al. In this beautiful paper that space works as an escape for these lizards, and space is what is causing that the cycle persists. So what I want to say is that dormancy can play the role of space as well. Of course, we are not thinking in lizards, but there are many bacteria that have this rock-paper scissors dynamics. For example, you can have a toxin producer, a susceptible and a resistant bacteria, and they can have a seed bank. So it's interesting to think what happened in this situation. So we have our model as before. We have a tournament rule, but again, this can be made much more general. It's a paper with all the members of my group. And what you have is individuals copy their type from the past, but sometimes they do this long jumps into the past. We prove convergence in the same scaling sense as before. And what you see is the game theory drift, the Fleming-Bio drift in the population genetic sense, and the dormancy part, right? So it's just that the pieces of the puzzle come together, and these things are very easy to simulate now, so we can see what happened. And what happened is quite interesting. So if the population size is huge, what you see is that the orbits persist, right? So this is the limit when the population size is gigantic. But then as the population size is getting smaller, you have that the orbits just crash, and one of the three individuals wins. However, if you introduce a seed bank effect, if you introduce dormancy, what you see is some coexistence occurring, right? So this is huge population size, but even when the population size is small, what you see is coexistence. And if the seed bank is really, really big, what you see is strong coexistence, right? So you have that things converge to these states, 1/3, 1/3, 1/3. And you can have it for larger systems and even larger systems. And here what you have is interesting coexistence where things disappear and they come back from that. So just to finish, some future work is we are trying to estimate this graph these coloring rules from data. We are thinking about endosymbionts and plasmids, because especially plasmids is something that I have been working a lot recently. And the endosymbionts part is with Mike, that he will discuss on Friday. I think coloring rules integrate classic population genetics with classic gain theory, so they are nice. And dormancy preserves diversity. So thank you very much.
Thank you for that mind-blowing talk. So I'd like to invite Emma to come up just to start to get kind of hooked up. And you have to join the Zoom and everything. Do you know about that?
Yeah.
Okay. But while she's getting hooked up, does anyone have a quick question for Adrian?
I sometimes in these cases I get the scaling wrong, and I want to have somehow a little bit stronger selection. I mean, what you assume you let selection, that like your selection intensity goes to infinity. If you don't do that, then these artificial processes have this weird property that if you go, for example, for a minority rule, and you select always the minority, suddenly kind of the minority is a big majority, and you can go extinct by these things. So do you know, is there a sweet spot in the scaling of the intensity of selection where, and this is obviously the case where everything works. But if selection would be a little bit stronger, how soon do you run into these weird things?
Yeah, that's a great question. So all of this is a game of scales. So the evolutionary scale is when you have selection going like 1 divided by n. And if you have something stronger than this, you just see the drift. And the other direction is terrifying. So I haven't put the other direction, but strange things can happen.
Let's talk about terrifying things.
Perfect.
Okay. Yeah. I'll let you have one more question, but you're new to the group. We're allowed only one question at this point in time.
Anything interesting about the deterministic of the paper scissors game with seed bank?
Yeah. So we haven't looked at that, but what happens is that there are no orbits. So everything collapses in 1 point, 1/3, 1/3, 1/3. So that the memory makes you go to that particular. Thank you.